There's one more chapter to our story of stellar evolution, and this one is the strangest one yet. When stars with more than 25 solar masses die, they don't simply end with a supernova and neutron star. Instead, they make an object that stretches our understanding of the physics of space and time, a black hole. The idea of black holes came from the general theory of relativity, Einstein's extension of the special theory that we saw earlier in the course. In this final lecture on stellar evolution, we're going to look at the general theory, the black holes they predict, and the ways we've observed these bizarre objects.
We've looked at the fate of stars that are smaller than 25 solar masses. Before we can see what happens to still larger stars, we need to introduce a new bit of physics. We've already seen the special theory of relativity. This describes how objects and forces behave when they move almost as fast as the speed of light. However, the special theory doesn't do well at explaining what happens when a body changes speed or direction. In other words, it doesn't describe accelerations. About a decade after the special theory came out, Einstein published the general theory of relativity. The general theory does describe accelerations in a way that was completely new at the time.
The key part of the general theory that we need to focus on here is how it handles gravity. Einstein argued that we could treat the force of gravity as a curvature of space and time. We normally think of space and time as not having a shape to them, but Einstein argued that we could treat space and time as bending when there's a mass nearby, and this bending is what we experience as gravity. Objects moving in a straight line have their paths bent because of the way space and time are curved, and that's why they accelerate under gravity. In this picture, we see the sun bending space around it, and the planets simply follow this curvature of space.
The idea that gravity is a bending of space and time sounds cool, but under most circumstances, the effects we see look the same as what we would predict from the traditional Newtonian picture of gravity as a force that we saw back in the chapter on motion and energy. However, there are a few things that really do look different if general relativity is true, and most of these have now been observed.
The first three of these are all closely related. In general relativity, time is affected by gravity as well as space, and this can be measured. The most basic change is that time moves more slowly the deeper into a gravity field you go. We can measure this effect on Earth, and we even rely on it all of the time. As we saw earlier, the Global Positioning System is a set of Earth-orbiting satellites that use extremely accurate clocks to help you measure your location. However, since the satellites are not on the Earth's surface, they run slightly faster than similar clocks on the ground. The GPS system has to correct for this change, or in a matter of days the locations would be out by many kilometers.
Another manifestation of this is the orbit of Mercury. Mercury is the closest planet to the Sun, and thus the most strongly affected by the Sun's gravity. In the 19th century, astronomers noticed that there were small changes in Mercury's orbit that couldn't be explained by Newtonian gravity. However, when folks calculated the effect of slowing time when Mercury was closest to the Sun, it fit the observations.
Third, light waves emitted in a gravity field are shifted to longer wavelengths as they leave the gravity field. We call this gravitational redshift, and it can be observed in the spectral lines of stars, especially stars with very strong gravity, like white dwarfs. There are a couple of other predictions of general relativity that are not tied to the slowing of time in gravity fields. The first of these was actually the first observational evidence for general relativity. A strong gravity field bends light in a process we call gravitational lensing. A few years after the general theory came out, a set of observations were made during a total solar eclipse. Below is a negative image of this eclipse. Dark areas in the image correspond to bright areas in the sky. What astronomers were looking for here were stars whose light was passing close to the sun. They did the observation during an eclipse because normally the sun's light drowns out any light passing close to it. What they found was that the position of the stars appeared to shift when their light path was close to the sun. Since then, we've seen gravitational lensing on a much larger scale. Light can be bent by entire clusters of galaxies. In this picture, the bright arcs are background galaxies whose light is being lensed by the cluster of galaxies in the foreground. Another prediction of general relativity is that rapidly moving massive bodies can generate waves in the fabric of space and time. These gravitational waves have only recently been directly observed. They were created when pairs of black holes collided together more than 1 billion light years away from us. We'll look more closely at black holes in the next few slides. We also have indirect evidence of gravitational waves from a pair of pulsars in a close orbit around each other. Because they're pulsars, we can measure their orbit from the changes in time it takes the pulses to reach us. And from this, we've seen that the orbit is slowly shrinking. They have to lose orbital energy to fall towards each other like this, and the only obvious way to do this is by generating gravity waves. Eventually, this pair of pulsars will crash into each other, though it's not expected to happen for another 85 million years. There's one more prediction of general relativity that we need to look at, and that's the formation of black holes. The more mass that's squeezed into a small volume, the more space gets curved. If the curvature is large enough, even light can't escape from the gravity well produced. Another way of saying this is that the escape speed from the mass becomes larger than the speed of light. This is what defines a black hole.
Since nothing can move faster than light, anything entering a black hole makes a one-way trip. Matter and energy can go in, but they can't come out. This means that the only information we can have about the matter that went into the black hole is its mass, spin, electric charge, and magnetic field, since these are the only ways that they can affect the universe outside of the black hole.
When a black hole forms, the mass inside collapses down to a point. However, this point is surrounded by a region of space from which light can't escape. We call the boundary of this region the event horizon. It's effectively the point of no return for a black hole. The distance from the center of a black hole to its event horizon is called the Schwarzschild radius. If you've got a black hole with a mass of 1 solar mass, then the Schwarzschild radius is 3 kilometers. So if you squeeze the sun's mass into a ball only 3 kilometers in radius, it would turn into a black hole.
Since the size of the event horizon only depends on the mass inside it, the Schwarzschild radius will be proportional to the mass and given by 3 kilometers times the mass in solar masses. We can use this to calculate the size of any black hole, provided we know how much mass is inside it. For example, a 4 solar mass black hole would have a Schwarzschild radius of 12 kilometers. If you want to see where this comes from, go back to the chapter on motion and energy and look up the equation for escape velocity. Then set this velocity equal to the speed of light, and that will give you the full equation for the Schwarzschild radius. When you put in the mass of the sun, you'll find it gives that radius of 3 kilometers.
Now you give it a try. See if you can calculate the Schwarzschild radius for a black hole with the mass of the planet Jupiter, which is 1,000 times smaller than the sun's mass. The strong gravity of a black hole can have dramatic effects on the objects close to it. For example, the gravitational pull goes up very rapidly close to the event horizon. This means that anything that gets close feels much more gravity on the side facing the black hole than on the side facing away from it. This is what we call a tidal force, similar to the force that raises tides in the Earth's oceans. However, near a black hole, this force is so strong that it can stretch the object into a long, thin line. This extreme stretching is sometimes called spaghettification.
We've already seen that time goes slower for objects deep in a gravitational field. Remember the orbit of Mercury? This means that something falling into a black hole would appear to take ever longer to fall as it approaches the event horizon. Of course, that's from outside. If you were the one falling, you would not notice this slowing of time. The strong gravity also bends the light around the black hole, creating extreme gravitational lensing. However, if you ever see the sort of lensing shown in this computer-generated image, you're probably too close to the black hole.
Once you move more than a few times the Schwarzschild radius away from a black hole, most of these strange gravitational effects get too small to notice, and the black hole's gravity behaves the way we're used to. So if the Sun somehow turned into a black hole, it wouldn't change the Earth's orbit around it. If no light escapes a black hole, you might wonder how we can ever find one. In fact, what we look for are the effects of its gravity on objects around it.
Generally, if matter is falling into a black hole, it won't fall directly in. The black hole is simply too small of a target. Instead, the infalling material goes into orbit and forms a disk around the black hole. Friction in this disk causes the gas to heat up to millions of Kelvin, letting it emit X-rays. So one way to look for black holes is to look for strong sources of X-rays. The image on the right shows one such X-ray source, Cygnus X1. This was the first black hole astronomers were able to identify.
If the black hole isn't accreting matter, then it won't be producing X-rays. Instead, the best way to observe it is to look for its effects on the motion of things around it. If a star is orbiting a high-mass, unseen body, there's a good chance that it's a black hole. Now that we know what black holes are, we can find out where they come from. To do that, we need to look at gamma-ray bursts. Gamma-ray bursts were first noticed by satellites searching for nuclear weapons tests. However, they were first studied by astronomers in the 1970s. They appeared as bright flashes of gamma rays, lasting 30 seconds or less, and coming from random locations around the sky.
Eventually, it was realized that they were mostly coming from very distant galaxies. The arrow in this picture points to a gamma-ray burst. Notice that it's brighter than the galaxy it's in. By combining the distance with the brightness, astronomers found that they had to be incredibly energetic events, releasing more than 10 to the 44th joules of energy just in gamma rays. This is comparable to the most energetic supernovas observed.
After the initial burst of gamma rays, these objects also produce light in X-rays, UV, visible light, and so on. The brightest of these was actually visible to the naked eye, even though it was over 7 billion light years away, halfway to the edge of the observable universe. By the 1990s, astronomers began to understand the connection between gamma-ray bursts, black holes, and the death of very massive stars. When a star has a starting mass of more than 25 solar masses, it develops a core that gets to more than 3 solar masses. That's so heavy that the collapse doesn't stop when it reaches the size of a neutron star. Instead, it crushes the core until it becomes a black hole. Since there's no bounce at the neutron star stage, no supernova occurs, and the rest of the star is not blown away in an explosion.
As we've already seen with neutron stars, when the core collapses, it starts spinning much faster. The same thing happens to the rest of the star as it falls towards the newly formed black hole, and much of this gas forms a disk around the black hole. Just as with protostars, most of the gas funneled through this disk will tend to be ejected outward in the form of jets. However, in this case, the jets are powered by the immense gravitational pull of the black hole. So these just burst out of the star's poles at nearly the speed of light, with a front of intense gamma rays just ahead of them. When we see a gamma ray burst, it means that we happen to lie along the path of one of these beams at the moment when the jets burst out. While matter slows down as it runs through the galaxy's interstellar medium, the light keeps going, allowing us to see the gamma ray burst even from billions of light years away. Now you should go ahead and fill in the last column of the stellar corpses table. Let's summarize the major steps in the evolution of stars of different masses.
All stars begin with the collapse of a molecular cloud core. The collapse heats up the forming protostar until it gets hot enough for hydrogen fusion to start in the core. Once stable fusion is established, the star settles onto the main sequence, where it spends the largest part of its life. The length of time spent on the main sequence gets much shorter as the star's mass goes up.
Low-mass stars, less than 8 solar masses, leave the main sequence and evolve into giants as their core contracts and heats up. After going through core helium fusion and double shell burning, the star blows off its outer layers in a planetary nebula, leaving behind a white dwarf.
High-mass stars between 8 and 25 solar masses evolve into supergiant stars instead of just giant stars. They go through several alternating steps of core and shell fusion, producing an onion skin core. When the core is converted to iron, it collapses to form a neutron star, while the shock wave produced destroys the rest of the star in a supernova explosion.
Finally, the most massive stars, larger than 25 solar masses, follow the same pattern as high-mass stars, except they produce a black hole rather than a neutron star, and this causes a gamma ray burst to occur without the occurrence of a supernova. Here's another Making Sense page. In this case, instead of setting it up as a table, we've created this flowchart for stellar evolution. In the boxes, you'll see the different stages in the life of a star. The arrows between these boxes give the processes that lead from one stage to a next. You should fill in these processes from the list at the bottom of the slide. Now you should try tackling another of these unseen companion problems.
You've got a B7 main sequence star that seems to be orbiting an unseen companion. The star is far away, so you wouldn't be able to see the companion if it's much fainter than the B7 star. However, from the orbit, you know that the unseen object has a mass of 15 solar masses.
So what kind or kinds of objects would fit this description? Have a look at what we know about it and see if you can figure out whether it could be a main sequence star, a white dwarf, a neutron star, or a black hole. You should make sure you use all of the information you've got: the mass, the limits on the brightness, and what you know about the properties of all of these kinds of stars. Also, be sure to say what's wrong with the choices you didn't pick.